Bom, entonces vamos a empezar hoy nuestra segunda clase de Bojana Femić. Muchas gracias, Bojana.
Bueno, sí, me pareció por tu tono que ibas a decir algo más, pues quedé esperando. Bueno, arranco entonces. Voy. ¿Sí? No se escucha. Bueno, sigo.
Sí.
Ok, gracias. Obrigada. Bueno, bienvenidos. Esta es la segunda charla de las 3 de este curso. Bueno, les digo que creo que hoy va a ser más corto, de unos 45 minutos más o menos. Y les advierto que estaba tomando mate uruguayo, lo que me puede... Oh, perdón. Sorry, so this... Okay. Sorry, so it seems that I have lost the connection for a moment. So I was saying that this talk would be shorter, around 45 minutes, and that maybe I will be going quicker because I drank Uruguayan mate, so please. Sorry, and please feel free to tell me that I can go slower. So I will here first recall what we did yesterday. So these are the 3 classes, first, second, third. Yesterday, we recalled categories and monoidal categories, and then we introduced bicategories and two categories. We saw some examples. We saw the bicategory of spans. We also defined pseudofunctors among bicategories, and we stated stratification theorems. So today we are going to see double categories. We're going to define them as specific internal categories. General internal categories we will see in the 3rd class, but today just this specific case for double categories. And the next topic today will be monads and two monads. These are two categorical monads. So let's begin with double categories. Well, first, let me recall that the
Bojana, you are not sharing your screen.
Oh. Thanks for telling me. Yeah. So now you see it?
Yes.
Okay. Thanks for saying that was because of the interruption of the connection. So, okay, I just recalled what we did yesterday and what we're going to do today. And let us start with double categories. I'm going to define them. So before that, I recall that a bicategory has these three levels. We have 0 cells, 1 cells, and 2 cells. Now in a double category, next what I'm going to show you is my, personal visual scheme, how I present the ingredients of a double category. So on this diagonal, I put 3 types of cells, which will actually show to be a bicategory. So first I have above on the top 0 cells, then horizontal 1 cells, and at the end squares, which are also called 2 cells. And of this diagonal, I have vertical 1 cells. So this is just to get the first feeling before the definition. Now comes the definition. A double category is an internal category in the category of categories. So this category I denote by cat1. For objects, it has categories, and for morphisms, it has functors. Now you don't know what internal category means, but I will show you in a moment. There was some sound, but everything is okay. Okay, I go on. So what is an internal category, particularly in the category of categories? Well, there are the following data. Firstly, there are 2 0 cells in the category of categories, so that there are 2 categories, which we denote by C0 and C1, and this is the usual notation. Then there are 4 1 cells, or 4 morphisms in the category of categories, that is, there are 4 functors. Firstly, there are these 2 source, which we call source and target. And this category C1 is usually called the category of morphisms, while C0 is called the category of objects. So source and target functors go from the category of morphisms to the category of objects, and this intuitively this is clear. Next is the unit functor that goes from the category of objects to the category of morphisms. What it does is that to every object, it assigns the identity morphism on that object. And lastly, there is the 4th functor, the C for composition, which goes from the pullback of C1 with C1 over C0 into C1. The category of categories has pullbacks, so that is why I didn't say anything at the beginning. But in general, an internal category is defined with respect to a category that has pullbacks. So here, cat1 has pullbacks, and we are okay. Now, this functor composition is required to be associative and unital with respect with this unit functor. So let's come back to my scheme that I was telling you. So I told you about these cells and how we call them. And in this square, I explain this most complex gadget in a double category, that is like a square. So in its vertices, I put 0 cells. On these 2 horizontal lines, I put horizontal 1 cells. On the vertical lines, I put vertical 1 cells. And the whole square serves as what is called the square, or a 2 cell. Now, what about these 2 categories, C0 and C1? Well, in C0 are the 0 cells and vertical 1 cells. I call them shortly 1V cells. So these 2, I'm not sure if you can see my mouse. It is showing the 0 cells and vertical 1 cells. They make the category C0, the category of objects, while C1 consists of, it is a category whose objects are horizontal 1 cells and whose morphisms are squares. So we have these 2 categories, C0 here on the left, so to say, and C1 on the right. Now I will explain these 4 functors. So, for example, source and target, they start from the category of morphisms C1. So on objects, to each horizontal one cell, you can look at this square F, one horizontal one cell above on the top. The source functor will give me back the object A. So you see the codomain of the source functor is the category of objects, is 0. And the target functor will give me back B, which is the codomain of the morphism F. So this is how source and target are defined on objects on horizontal one cells. Now, source and target on morphisms of the category C0, C1, and that is on the squares. So look at this square alpha. Source will give back this vertical one cell V. And vertical one cells are morphisms in the codomain category C0. While the target functor to the square alpha will give back the vertical one cell zeta. Okay, so this explains how source and target act on objects and morphisms. Now the identity functor U, it goes from C0, so from 0 cells which are vertices in the square, and morphisms vertical one cells, and it gives, well, to object A, to an object A, it gives the identity horizontal one cell. So imagine that this F is identity on A, and in this case, B will be equal to A. While on morphisms, so for a vertical one cell V in this case, the functor U will give the square alpha, which will be identity on V. So remember that above F is identity when U acts on objects, and below G is identity on A prime in this case. And now U acting on V will give me for Z again V, and we will have a square. We will have the square, which is kind of horizontal identity, how to say. Good. And now the composition functor. What this means, what does it mean, this pullback? Now, I would kind of like that you see, you can see me, right? In some window, I have prepared these two squares. Can you see the squares in my hands? I don't get any feedback,
Yes.
but
Yes.
Thanks. Good. So what does it mean, this pullback? See that pullback is defined on C1. So that's this category of horizontal one cells and squares. So imagine that beside this square alpha, we have another one in the horizontal direction. So like this. Then if this is your left, right? I just needed to check if it is the mirror, right? So if you go from left and this is your F, F gets into B. So this common vertex for the continuation, so this is firstly one cell F and then G. Then the pullback goes over the object B. I mean, it's very intuitive. So this C gives me the composition of horizontal one cells, okay? So this is how C acts on objects. And on morphisms, recall morphisms here are squares. So I will have one square alpha and then another one beta. So the composition is going to give me this total square. It's going to give me this total as the end object, right? So this C defines the horizontal composition. And you have from the property that the C is a functor when it acts on two squares, which are two morphisms, then C preserves strictly their composition. So the horizontal composition of two cells is strictly associative, and of course, it doesn't have any other choice because, yeah, we are just in a one category of categories. On the other hand, the fact that C0 is a category It means that it's morphisms which are vertical one cells. They have also their composition, and then it induces also the vertical composition. Okay, so it only speaks actually about the composition of the vertical cells. But if you look actually at the category C1, where morphisms are squares, then they also can compose vertically. So just from the ordinary composition in the category C1, where the C functor gives the horizontal composition. So as you see, there are kind of, I don't know, not too many structures, but there are more structures. So you have to keep track of what is what, which piece of information gives me which other information and so on. Okay. Now, what is a pseudo-double category? A pseudo-double category so it is introduced as a pseudo category internal in the two category of categories. This cat2 is the two category of categories, functors, and natural transformations. And this term pseudo category internal in the two category was coined by the Portuguese Nelson Martins Ferreira in his paper. I don't remember if it is internal. I don't remember. Pseudo categories, I think, is the name. But throughout, I will not use the terminology pseudo category. Rather, I will just say internal category in the two category. Because already when I say internal in the two category and not in one category, I know that I will have more structures. And I don't want to complicate with the name pseudo category. Okay, so now let us see what is the difference, because a common double category, which can also be called strict double category, and a pseudo double category. So firstly, we have the same as before, categories C0 and C1 as 0 cells now in the two category of categories. We have 4 functors, source and target, unit and composition, which are 1 cells in the two category of categories. But now, since we have this internalization in the two category, then we have 1 degree more, 1 dimension more to use, and so the associativity of this functor C and the unitality with respect to U now is not anymore strict, right? But rather, we require additional natural transformations, alpha, lambda, and rho, which are 2 cells in the two categories, which control the associativity of this C on the pullback and unitality with respect to U. And now this alpha, lambda, and rho, as always, need furthermore to satisfy the pentagonal and triagonal equation. I don't write them out. It is a nice exercise to see how it looks like, but for me it's now important that you see the concept. And you can immediately see the difference between a strict double category and a pseudo double category. And it is that, the crucial thing is this C, that its composition is not anymore strictly associative. So that means that the horizontal 1 cells, their compositions and the compositions of squares will not anymore be, that is only on the level of horizontal 1 cells, their composition will not be strictly associative. And now digression. Yeah. A digression, the same happens in a bicategory with respect to a 2 category, That's on the level of 1 cells. In a bicategory, you have that their associativity is not strict, but up to an isomorphism, where here happens the analogous thing. Now here I give you an example, firstly of a bicategory, and then I incorporate something else to show how it makes a pseudo-double category. Well, firstly, this is a bicategory that everybody here knows, but maybe you just didn't use the terminology that it is a bicategory. So for 0 cells, it has algebras. For 1 cells, it has AB bimodules. And for 2 cells, this bicategory has bimodule morphisms. So recall that if you take 3 bimodules and you tensor them over the respective algebras, you know that this associativity is not strict, but up to an isomorphism. So it shows you that we indeed have a bicategory rather than a 2 category. So this is just a bicategory. But now you may see that when we consider this bicategory, we are neglecting, we are omitting one important algebraic structure here, and that is that of morphisms of algebras. So we speak here about bimodules and bimodule maps, but we don't speak, and also we speak about algebras, but we didn't incorporate algebra morphisms. Well, this is what a pseudo-double category does. It incorporates this other type of morphisms that in a B category that incorporates bimodules remain neglected. So here comes the pseudo-double category, the corresponding one. As I told you, on this diagonal, I put this bicategory. So for 0 cells, I put algebras. For horizontal 1 cells, I put bimodules over these algebras. And for 2 cells, I put bimodule morphisms. Yes.
Algebra morphisms can be incorporated in this category, putting B as an AB bimodule and using the left action of A, using that morphism. Then you can create artificially morphism there.
I see.
Using B as the AB bimodule, which is the morphism, proper morphism in this bicategory. Isn't
but
it?
Sorry, how do you connect A and B? So, at the first place, how do you connect A and B? I mean, your B is what from the beginning?
Well, if you have morphism phi from A to B, then consider B as right.
Okay, but that's what I mean. I want to stop you immediately, because where does this phi live? And I'm telling you that this phi lives here in vertical 1 cells, and it needs to be algebra morphism.
No, yes,
I mean,
yes. This is
what I'm going to say.
This is how we learned about this, but you are presenting another perspective on this. Okay.
Yeah, okay. Sorry now, because I cannot see who is it. I just guess that I know who is it, but I don't see
it's
you.
me, Eliezer.
Yeah. Hi, but I don't see you. Okay.
Hi.
Yeah, thanks for the digression, and possibly to help, your students or somebody around who thinks the same way as you, but as you say, I'm presenting this in another way, okay? So precisely what you were saying, I need that phi or phi, okay? So it is incorporated here in the vertical 1 cells. Good. And now below I will show more. And yeah, this star stands for another phi that I wanted to add here, but now I see that I forgot to add, but nothing, it's not important. These were here, it was just written here, the 3 bimodules and how this associativity is up to an isomorphism. It's the only thing that I wanted to add with this red asterisk. Okay, so this is to show this that I have just commented, that on the level on 1 horizontal cells, bimodules, they are not strictly associative. This tells me that in the total, I will have a pseudo-double category and not a strict double category, okay? And now, this gadget, these algebra morphisms that we were omitting, if speaking about bimodules and bimodule maps, they come at this place of vertical 1 cell. And now comes this, what you were saying. So this is 1 square. Let us apply our example to this square. In the vertices are 0 cells, which are algebras. On the horizontals are AB bimodules, bimodules. If M is an AB bimodule, I write first B and then A, so this is the other way around. And N here is an A prime, B prime bimodule. And now on the verticals, I put algebra morphisms from B to B prime and from A to A prime. And now the 2 cells, they are bimodule morphisms. That means that this alpha, like looking from the point of view of the category C1, alpha will be a morphism from the bimodule M to the bimodule N. And now alpha, I'm saying that it is an AB bimodule map. But I first need to say how this N in the codomain is an AB bimodule. And this is done precisely along this F and G. And precisely because of the fact that F and G are algebra morphisms, this will give me B module structure on N and A module structure on N in this way that I wrote down. At the bottom. Okay. So now, based on this example, 2 comments. Firstly, in every pseudo-double category, there is a bicategory. How? Well, for vertical morphisms, take only identities. And correspondingly, for the globular 2 cells, they are called globular, they are of this type. So you take for the verticals the identities, and then the squares are of this form, where above is some F, below is some G, and these are called globular 2 cells. And there you get a bicategory. Well, the 0 cells are the vertices, 1 cells are these horizontal 1 cells, and since in the squares verticals are identities, you get just an ordinary 2 cell in your bicategory. And this pseudo, this weak, property in a double category corresponds to the weakness in the bicategory, and that is on the composition of 1 cells, as we commented before. And now this bicategory that we obtain this way is called the horizontal bicategory of the pseudo double category, and you can denote it like that. The other way around, each bicategory can be embedded into a pseudo-double category. Well, in the obvious way. So just define your vertical morphisms to be all identities and define the squares only of this type. So this is, of course, much smaller than some general pseudo-double category. So we have kind of a junction, we have the forgetting and embedding here. And from the end of the previous talk from yesterday, we can recall at this place that every pseudo-double category is double equivalent to a strict double category. So this is good to know for some work with double categories. Okay, so this finishes the first topic of today's talk. And now we go towards the second one, which is about monads and 2 categorical monads. Well, firstly, a monad in an ordinary category, which even doesn't have to be monoidal. Well, a monad in C consists of a functor T on C, this is an endofunctor, and 2 natural transformations, mu from T composed by T to T. So we can call it a multiplication. Sorry. And eta, it goes from the identity functor on C to T itself, so that these 2 laws here should hold. Now, usually these axioms are written in square diagrams, but since I worked with braided monoidal categories, I like these string diagrams, and now I will explain how I use them. Normally, these string diagrams are used in strict monoidal categories, and thanks to the strictification theorem, we can always go to an equivalent strict monoidal category, and there, first let me tell you that these diagrams now are considered in the monoidal category of endofunctors on C. The monoidal structure is given by the composition of these functors. and the unit by the identity functor. So in these strict diagrams on the top, I read them firstly from top to bottom. Here the axioms are symmetric, so it doesn't matter if first is left or right. And now to tell you that on the top, I put objects of the category, and on the bottom, the codomain. What I say? At the bottom also objects, but the codomains of the morphisms, and strings stand for morphisms. So the objects here are functors, T is functor, and the morphisms, these correspond to natural transformations, which are morphisms in this category of endofunctors. Well, the only here two natural transformations that we have at hand are the multiplication and the unit. Well, this symbol, which unites two strands going out of T, stands for this mu, multiplication. So the first axiom speaks about the associativity of mu, and this circle out of which a string goes out is the functor eta, since it starts from the identity functor. This is natural transformation eta. Since it starts from the identity functor, I don't write the object, and the outcome is T, and here the multiplication. So the second axiom speaks about unitality of mu with respect to eta. Good. Okay. Now, an example. If you have a monoidal category C and an algebra inside, it determines a monad by tensoring with A. So then the multiplication of A gives rise to the natural transformation mu, and the unit of A gives rise to this eta natural transformation. Morphisms of monads. As monads here are functors of C, then morphisms will be natural transformations from a monad T to a monad P, such that these natural transformations are compatible with the multiplication of the two monads and with the unit. So these are really the usual axioms. And now, well, I just wanted to recall this in order to facilitate understanding of two categorical monads. So two monads are monads in two categories. A two monad consists of, firstly, I take a zero cell A, then a one cell T, which acts from A to A, and finally two cells. One is mu from TT to T, and another one is zeta from the identity of the zero cell A to T. And observe that I use this different arrow since I'm denoting two cells, and they are not anymore just functors composing, such that, well, I write in the same way the diagrams for associativity and unitality, but note the shift in dimension in the meaning of diagrams. What does this mean? Well, in the same way how monoidal categories give rise to bicategories, this delooping of a category. I don't remember if I told you, that's like a new terminology that I discovered recently. If you from a monoidal category defines a two category with a single zero cell and then object and morphism, this is called delooping of the monoidal category. So there you saw that objects take role of one cells and morphisms of two cells. With the same logic, I apply the string diagrams in two categories. So these on the top here, I put one cells, T here is one cell, and now the strings stand for two cells. So I'm not writing out the zero cells, okay? But when I compose my one cells, I need just to pay attention that they are composable. And of course, T is just an endo cell, so here we don't have to worry. Okay, now an example. This is to connect with an ordinary monad on a one category. So if T is a monad on the category C, it is actually a two monad, particularly in the two category of categories. So why? Firstly, it needs to be a one cell on the same one endocell over one fixed zero cell. So a zero cell in the two category of categories is some category. Well, I take the category C for this zero cell. And then T as one cell is a functor. Well, yes, indeed, it is a functor as an ordinary monad. And being an ordinary monad, I have two natural transformations, mu and eta, which indeed are two cells in these two categories, and the axioms are the same. So you see how this works. So you see that this definition of a two-categorical monad is really a natural two-categorification of an ordinary monad. Now, here I will present another kind of example or construction. So here we can see how strict monoidal categories become two monads or give rise to two monads. So let's see, be a strict monoidal category. And let us set for T the following functor on the category of categories. It is just C Cartesian product with, right, here we take some argument. How does this functor act? For an object in here that is for a category M, T of M is just C times M, so it gives another category. And for a functor F among two categories M and N, so this functor is a one cell in the category of categories. T of F is this C times F, where C acts as identity on the left coordinate, and on the right just F is acting. So from here, this definition, it immediately follows that when T is applied on the composition of two functors, it is the same as composition of these two images. So that T is indeed a functor on the category of categories. Well, then actually T is a two monad in the two category of categories. So we saw how it is a one cell here, so a functor, and the zero cell is this cat1, the category of categories. And now what about two cells? Well, for mu T, we will put the tensor product from our C, which is monoidal category, and then times something. So then in total, this is a natural transformation. And for eta, which should go from the identity on our zero cell, which is cat1, into T itself. I evaluated already as the specific category, which is the trivial category, the star. So then when I compute what this gives me, identity is just the star, T of star is C times star. So in total, I will give this eta evaluated on the star. I will give it by the unit functor U from the trivial category to C, which determines the unit object in my monoidal category C. So here C times star gives back just C. So indeed we have here this unit functor. And so mu and that are natural transformations, and as such they are two cells in the two category of categories. Now, what about and why strictness of our monoidal category C? Well, for two monads in two categories, we have that the associativity is strict. Associativity for mu on T. And this corresponds precisely to the strictness of the tensor product in the strict monoidal category. Okay? In general, one can consider two monads in bicategories, so where the composition of one cell is not strictly associative. In this case, instead of two monads, they are called pseudomonads. So this term, this notion exists. And then your category C doesn't have to be strictly monoidal. So to sum up, cat1 is a category. As such, it is a zero cell in the two category of categories. T is a functor, so it is a one cell in cat2. and mu and t, which we gave like this, are indeed natural transformations, and as such, there are two cells in the two categories of categories. So here we saw how strict monoidal categories give rise to two monads. Before going the other way around, one small observation: these two monads has this property that when I apply to a star, then it gives me back just C itself. Okay, this is one important observation. So now for the converse, we may observe that any two monad T which acts on the category of categories, and this is a two monad in cut 2, and which additionally satisfies this property that it is given by T of star times something, it yields a strict monoidal category T of star. Now I will comment why I need to add this property that T is of this form. Well, let us define T of star. Let us denote it with some C, some category C. Then when you have a two monad in this composition T with itself, TT, how can we go from TT to C times C? Well, firstly, I evaluate TT in this trivial category star. Then since T of star I call C, I get to T of C, sorry. But now, without having this condition, I cannot go on. And precisely because I know that T is given by C times something, this T of C gives me that I end up in C times C. So now I can say that I have some functor defined on the Cartesian product of C with itself. And then I get what will be the tensor, the monoidal structure on T of star, which is C. Okay? Good. So far, that's it. And now I want to tell you about the two category of monads. I'm just a little bit looking at time because I have a choice. I can do it today or, yeah, never mind. Let's just go on. Let's do it today. So there is a two category denoted like this of two monads in a two category K. Okay, so we are really going, it's getting a little bit involved. Well, this two category of monads in a two category K consists of the following. For zero cells, we just take two monads. So we saw they are given by zero cell A, a one endocell T on A, two cell mu, and two cell eta. And now for one cells, it's a little bit more complicated. One cells are pairs, X and psi, going from, this is shorter for a monad T on A, into a monad T prime on A prime, where now X goes from zero cell A to A prime, and it is a one cell, and psi goes from this composition T prime X into XT. Observe that this is well defined because X starts from A, ends up in A prime. This composition I'm reading from right to left. So X starts on A, finishes in A prime, and then T prime acts on A prime as an endocell, so this makes sense. And here, analogously, T acts on A, it ends up in A, and then X starts from A, so this is also coherent. And now the axioms that this pair should satisfy are these two. So from T prime X, firstly psi is acting here on the right, then again psi here, and then multiply here, it is equal to this. So this is kind of some naturality. If you go to the example of when K is induced by the monoidal category, you can take for psi to be just the braiding, and then this is nothing but the naturality of the braiding with respect to the multiplication, and the other axiom is the neutrality with respect to the unit. Okay, so we have these two axioms, sorry, for one cells, and now finally two cells between these two one cells are given by just ordinary two cells in K. And now these two cells theta should satisfy this axiom. So it's again like some kind of neutrality that theta passes this way. Okay, so this is how these two categories given. I should tell you the identities and the compositions. And for that, I go to this other slide. The horizontal composition, actually just composition of one cells. This horizontal is too much here. So if I take a pair x psi acting like this, and psi is then acting like this, and another one y with its psi on t prime, then this psi for t prime acts like this, I define their composition as a new pair where on the level of objects it is just composition of one cells x and y, and the two cell I define like this. So here you apply psi from t prime. Recall that it acts from t second into t prime this way, and then there acts this psi from t prime to t, so to say. So this is how it is defined, and one shows that this is well defined. And now to tell you that vertical and horizontal composition of two cells is given just as in K. So for example, as here I have written what induces the horizontal composition on two cells, the horizontal composition in two cells in K is given just by, horizontally, you would act with one theta 1 on Y here on the string for Y, and with theta 2 on the string for X, and then they just pass along, so the axioms will be satisfied. And for vertical composition, it's even easier. If you look at this bottom axiom, then vertical composition in K will mean you put one theta below theta 1 and then theta 2 below, and they also satisfy the axiom. And here also to say that the identity one cell on a zero cell AT is given by the pair. The one cell is just identity on A, and the two cell is just identity on T. So two cells should act on the composition, but since at the place of X is just identity on A, then I neglect this X, and then I take just the identity on T. Okay, so this is how this two category of monads in a two category is defined. And today we don't do anything else with this two category. And now we go to T-algebras. So this is, okay, so another topic and connected to monads. This is connected to monads. We go back to ordinary monads, T on ordinary categories C. So for a monad T on C, a T-algebra is an object X in the category C with a morphism mu from T of X into X, a morphism in C, such that these two axioms should hold. So recall that here multiplication stands for multiplication from the monad T, and then this here stands for this action mu. So this is the same as acting and then acting again. And lastly, unit on T and then acting is just identity on X. Well, this looks familiar. If you consider that monad induced by an algebra in a monoidal category and given by just tensoring with A, then a T-algebra is precisely an A module in C. So imagine here that, well, this nu is this morphism, and so you have these axioms. Okay, so this is immediate. And now I recall this definition in order for you to understand the motivation how to define T-algebras for two monads. And this I define here below. So for a two monad T given on the zero cell A with two cells mu and eta, a T-algebra is given by a one cell X, which starts from any zero cell, possibly different than A, and it ends up in A on which T acts. And also it is given by a two-cell nu that goes from the composition Tx into X, so that the analogous axioms as the above ones hold. Again, observe the shift in dimension when we apply these string diagrams in two categories. Now we will do a similar exercise as before, and we will relate T-algebras on two monads versus C module categories. So this is a topic that I guess Martin will speak about in his course. So again, let C be a strict monoidal category, and let T be again this functor, this actually two monad in the two category of categories, which is multiplying with C. Then a T-algebra, okay, this is just the repetition that the T-algebra is given by X, nu with two axioms. And now let us suppose that this X is of this particular form, multiplying with X applied on star. And so that A and also A prime are equal to the category of categories. And set X of the star to be some category M. Then, now I'm going to translate the axiom for a T-algebra for this, in this case. So then X is given by M times, and as such it is a functor, so a one cell in cat2. Then nu, well, see, it is given by T and X, and now T is this one, C times something, and X is M times. So I end up with a natural transformation of this form, and as such it is a two cell in cat2. And I also have these two diagrams, which before I wrote in string diagrams. But in order to connect with something that you visually can recognize, I write here these two diagrams in this other way, as square diagrams. Well, recall that before we had this multiplication on the monad and then act. Well, this here is the role of that is played by this tensor on C and then act by nu, and on the other way act and then act. So you can recognize this as the definition of a C module category. And here similarly the unit property. So we get that X applied to star as a category is a C module category. Conversely, if you start with M being a C module category, it yields a T-algebra X, where T is given like C times and X is given by M times. Okay, so here we see the relation between strict monoidal categories and T-algebras with C module, with two monads and C module categories. Okay, I didn't say it properly, but you know what I mean. And here comes the last topic for today's talk, and I'm approaching the end of the time, but we started a few minutes later, so I'm just in time, and it's not 45 minutes, as I said at the beginning. So the last topic here is to show you how two monads can actually be seen as lax functors. We defined yesterday pseudofunctors among bicategories. And now I will show you, there is a slight difference what a lax functor is. So this slide will be almost a repetition of the definition of a pseudofunctor, and I will stress the differences which makes it lax and not pseudo. A lax functor consists of an assignment that to objects gives another object in the codomain bicategory. It also has functors indexed by objects, pairs of objects A, B. So they assign these one cells, and on two cells they behave like that because they are functors. And now moreover, and the difference comes at this place, moreover there are two natural cells, which I don't require them anymore to be isomorphisms. They just go in one direction. Well, there's this psi and this theta. So this is the compatibility of F with the composition of one cells and with the identity one cell. And they also need to satisfy this hexagon and two squares. Good. So now we will apply a general definition of a Lax functor to the specific case when my source bicategory is the trivial bicategory. So I recall you what it consists of. It has the only zero cell, which I also denote by star. It has the only one cell, which is identity on star. And it has the only two cell, which is identity on the identity on star. Okay? So first we have this assignment, which to each object, well, to the unique one, it gives a zero cell, an object. So let us denote this unique image object by A. Then we have family of functors, which now end up being one and only functor. And now to one cells, and we have only one cell, only one cell. It assigns the image one cell, let us denote it just by T. And to the only two cell, it assigns, which is actually given by identity, it assigns identity. Well, we know that it will be identity on T because this F is a functor. So we have this preservation of identity morphisms. And now let us translate these two cells. So we have additionally two cells. They go from F of identity because now these F and G are the only one cell which is identity. And F of identity was just T, the one cell T. So this psi is a two cell from T composed to T into T itself. And let us denote it now by mu on T. And similarly, zeta, it is identity on F of star, but F of star was just A. So it goes from the identity on A into F of identity, which is T. And let us denote it by eta T. So now it really reminds of a two monad. And now let us check the hexagon and two squares. Well, here is the hexagon. And if we here consider that this K is a 2 category and not a B category, then alpha, lambda, and rho will be identities. So in this hexagon, I actually have just a square. And recall that this psi here was our mu. So multiplication for the monad. And when you check now this axiom, you see immediately that this is nothing but the associativity of the multiplication on what will be the two monad. And here we have that this theta, which was actually this eta 2 cell, and then multiply is equal to the identity and the other way around. So we really see that the Lax functor, which acts from the trivial 2 category to any 2 category, gives a 2 monad in K. This is something that was observed by Benaboú. Sorry that I now see that I didn't write it out, but actually it is due to him. And I think it's like on pages from 39 to 42, something like that. Okay, so this finishes the second talk. And I will be glad if you have some questions to respond them.
Excuse me, one question.
Yes, please.
The category of correspondence, that category in which 0 cells are algebras and 1 cells are bimodules. If you take
where we spoke the last time in double
there, which is a AA bimodule, and then this two monad is an A ring. Could if you two monad as one cell.
Sorry, can you just repeat, because I was thinking one while you were speaking other. Can you, sorry, please repeat.
Yes, again, that category where 2 cells are algebras, 1 cells are bimodules, that double category you presented. If you take a 2 monad there, which will be a 1 cell between two, the same 0 cell from A to A, isn't it? As far as this. yes, then it will be an AA bimodule. If it is a monad, this
Yeah.
will be a ring.
Yeah. I never, thought about that, but definitely it gives something in this direction, as you're saying. Yeah, that's a nice point.
Yes, and another question, which is more speculative. Have you
Yeah.
thought about because we have the theory of bimonads and Hopf monads. When you think
Yeah.
about two monads and think about this lifting of the tensor, the monoidal structure to the Eilenberg-Moore category, what do you expect if the monad is tensoring for something, this object will be like what, Hopf algebroid or something?
Yeah. First to tell you that, I know these results in the classical case from this Murdik, I don't know how you pronounce it, no, the Dutch scientist from
Yes.
Holland. And, but I also have an impression that I was reading this two categorical version, So what you are asking, I actually have a feeling that I have seen that it was done, but since it was never really my, concrete topic of research, I never really, studied it thoroughly. But I have an impression that somebody did it. So now, which results did they get? I don't know to tell you because I tell you it was not my focus.
Okay.
But later I can think of it. I can think of where I saw it, and I can search a little bit and then see.
Okay, thank you very much.
Yeah, there are even just some Chinese. I needed to make some, how do you say, to write about those works of them. So then I saw that they were doing this theory of lifting to Eilenberg-Moore, but I now forgot if it was really too categorical. But okay, I know where I could search.
Okay.
Thank you. Yeah,
Thank
but
you.
I'm afraid it's already done, so to say. But I may see what it is done, so to see if there can be done something if it is not done, right? So thank you for pointing this out.
Okay, thank you, Bojana. We'll see you
Thank you
next
for,
Thursday. Yes.
okay. Ciao, ciao.